I get everybody's attention? Can you hear me in the back? Hear me in the back?
Yeah, sorry.
That's all right. I'm happy to introduce our speaker today, Dr. Núñez Ocasio. She's coming here from NCAR, where she's an ASP postdoc in MQ. She got her PhD from Penn State and her bachelor's in theoretical physics with a curriculum focus on atmospheric science from the University of Puerto Rico at Mayagüez. Yeah, her background, she focuses a lot on MCSs, African easterly waves, tropical cyclogenesis, African weather. And our link is she spent last year in Japan launching radiosondes for the preset field campaign, and then forecasting and doing important mission roles for the CPAC-CB campaign off the west coast of Africa, where we finally got to, I think, meet in person for the first time during that campaign. So she's going to be presenting on a lot of that work, including her open source MCS tracker that I imagine many people are very interested in here. Outside of the science, she serves as an ambassador in the AMS committee for Hispanic and Latinx advancement. And fun fact, she's really into true crime podcasts. So take it away, Kelly.
Thank you so much, Angela, for the invite and for the introduction. And I'll just move over here. Yeah, so it's been great. My visit here so far, very welcoming and warm department. I'll be sharing today some of my past work and how that kind of motivates what I've been working on in current times at NCAR. So related to the multiscale nature and moisture dependency of tropical cyclone formation. So in the latest tropical cyclogenesis literature review, they define tropical cyclogenesis as the process for which a one-core, non-frontal synoptic scale cyclone organizes and basically collocates with deep convection, and then a well-defined center comes about. And so when they talk about this synoptic scale cyclone in the Atlantic, most often than not, this is African easterly wave. So this synoptic scale cyclone can be aided by or seeded by African easterly waves. So in a very general definition, an African easterly wave is a synoptic scale disturbance that arises over the summer months over Africa and then propagate westward into the Atlantic. And so by themselves, they're an extreme weather event. They're important because they are the seed, they can be seeds for tropical cyclones, but I always like to highlight the fact that they themselves are extreme weather. I remember back when I was in Puerto Rico and I was going into my calculus class, and there was this one time that I had water up to my knees because of the passage of an African easterly wave. So it is really important to study both waves because they're seeds, but also they're extreme weather by themselves. Now going back to tropical cyclogenesis, we know a lot of the formation of a tropical cyclone, but still we have challenges. It's still an open question, an open topic, and it's because of these challenges. And I think it comes to two things. First of all, we have a limited understanding of the interactions between the mesoscale processes and the actual tropical cyclone seedling. But it turns out that these interactions are in large part driven by water vapor. And as we can see here, which is actually one of the imagery that comes from this department, in this total precipitable water animation, water vapor varies greatly in space and time, and this is a motivation for a lot of us tropical meteorology folks. And so, in trying to understand tropical cyclogenesis, I started by first looking at the large scale. So at the large scale, how does the monsoonal environment over Africa actually relate to tropical cyclogenesis likelihood? So in this work, we identified what we called main key predictors of a possible subsequent event, a subsequent tropical cyclone event. And so this is what we found. in a very general sense, we found that those waves that do end up becoming tropical cyclones propagate over Africa in a more favorable environment. And that favorable environment over Eastern Africa means that we actually find stronger monsoonal flow over Africa. We also find that there's stronger convergence over the Amera Mountains and also over the Ethiopian highlands. So these are regions of orographic uplifts that not only mesoscale convective system arise, also perturb and initiate easterly waves. We saw that over Western Africa, again, we had that stronger monsoon flow, but also larger quantities of moisture associated to the monsoon. And we also found that there was a more intense and extended African easterly jet. So in addition of these main key predictors, we also found a relationship between where they actually originate and their likelihood of becoming tropical cyclones.
For the stronger convergence, what level did you see that strengthening? Was it across the entire depth, or were they particular levels?
That's a good question. So I looked at 850, 900, and 700, and there was convergence being greater at those levels, yeah, for the developings. So going back to where they originate and their likelihood of genesis, what we actually found is that those waves that initiate over Eastern Africa, so over the Ethiopian highlands, these waves are actually more likely to become hurricanes than those that originate either over Central or Western Africa. So we argued that this possibly means that these waves spend more time interacting with the monsoon and the convection associated with the ITCC. So in a sense, they're more prepped to be potential tropical cyclogenesis candidates. Now, this doesn't make the problem any simpler because previous work has showed that African easterly wave intensity forecast has low skill when we have a lot of water vapor downstream of the African easterly wave. So if this is the case for a low skill forecast, then this is the case for genesis, because we're seeing that those cases that do become hurricanes are more likely propagating in a more moist environment. So it's telling us why this is so hard, but we're really not finding how to fix it here. So that was looking at the large scale and how it relates to the tropical cyclogenesis likelihood. Now we focused on, okay, how does the mesoscale relates to the actual tropical cyclone genesis? And so for that, I used a combination of tools. The first one being TAMS, which Angela mentioned. This is the tracking algorithm for mesoscale convective systems. And so TAMS provided a data set of MCSs. Then I matched with an existing African easterly wave track data. So in that way, I developed a data set of what I called coupled systems. So I match all the MCSs to their associated African easterly wave. And so these are the main results of this work. So this is what we found. So here on the left is the conceptual diagram for what we found for the developing composites, for those systems that do become tropical cyclones. And then on the right for the non-developers. So here the wave is identified with this inverted trough, so the black triangle. The cloud is the convection, and the arrows here are showing you the speed of the system. So this is what we find. We find that developing waves, those coupled systems associated with developers, the convection is more likely to move not only at the same location of the vortex, it also moves at the same speed. So they were more likely to be completely in phase with the circulation. unlike the non-developers, we actually found that the convection associated with the non-developers was more likely to be moving south of the African easterly wave, and not only that, a little bit faster. So it was more likely that the convection associated to non-developers was out of phase with the vortex. So it's not supplying that additional heating from that vortex stretching, so it's not feeding back to the wave. And so basically, with this observational evidence, for this I just used satellite imagery and reanalysis, I argued that it could be potential observational evidence that moisture vortex instability from Angela here could actually be an instability that is happening for genesis in the eastern Atlantic.
Kelly, if you don't mind, I just have to ask, given that, is there a moist PV tower distinction between the structure of these developing waves nurtured over the Ethiopian highlands and the ones that develop in situ in West Africa?
That is a great question. I personally haven't seen the moist PV structure from those easterly waves from the western. But I will say this, in a very similar paper by James Russell 2020, he also shows a moist PV vertical stack structure like the one that Angel proposes. So very similar conceptual models. So as you probably have heard by Angel himself, in this instability, what he argues is that when you add that moisture towards the center of the circulation, it aids convection to grow very near that low-level vortex. And so that vortex stretching then aids the circulation, and it's ultimately a positive feedback between the wave and convection. So the closer it is to the circulation, the better chances it is to aid growth. So before I move on into showing you today what I'm working at NCAR, I wanted to go over a little bit onto other theories as we know them. So I just went through moisture vortex instability. We also know moisture mode, and what we know from a moisture mode by a very simple definition way back with Raymond and Fuchs' work is that it's when precipitation is a strongly increasing function of saturation fraction, and when convection acts to increase the saturation fraction. And more recently, by Angel and his research group, they pinpoint criteria that we can test whether or not a system is behaving as a moisture mode. And so those criteria are described here. The first one being moisture anomalies must be correlated with precipitation anomalies. The wind temperature gradient balance must be dominating the temperature changes, and moisture controls the thermodynamics of the system. And so the idea with these theories and bringing them into this talk today is because rather than revisiting the theory, what I use is I take these theoretical tools and I try to see whether or not they can become diagnostic tools for tropical cyclogenesis. Can I use these theories to help me understand the growth of a tropical cyclone in the eastern Atlantic? And so, full disclosure, and I always like to say this, I'm not saying that dry dynamics aren't important, right? They're very relevant and applicable. We know that barotropic and baroclinic instability are still playing a big role in the energetics of African easterly waves. What I'm proposing here in many recent work is that perhaps moisture becomes a more relevant role the closer we get, at least for these waves, to the western coast of Africa and closer to genesis. So at NCAR, I've taken all of these ideas and really focused on trying to understand the mechanisms that lead to genesis from the moisture perspective. So I've made use of a weather and climate model, the MPAS, to simulate a past case of an African easterly wave, and first make sure that this model is capable of simulating tropical cyclogenesis, and then go into the actual science and investigate the role of moisture in the mechanisms that lead to this specific case, which is Hurricane Helene back in 2006. And so today I'll focus on the fun stuff, I'll say, which is the mechanisms that lead to genesis. So the model for prediction across scales. Like I said, it's both weather and climate model, meaning that you can run it globally with coarser resolution, with convective parameterization, but also at smaller scales, convection-permitting, regional type of configuration. In this case, I'm going to show you today results from global simulations using convection parameterization and two different data sets to initialize. So the ECMWF integrated forecast system and the NCAR forecast, global forecast system. So I initialize MPAS at a day where the wave was already existing over Africa. It so happens that in WRF and in MPAS, I'm not able to initiate this particular wave over Eastern Africa. There's a lot of topography, surface interactions going on that the model is still not capable to resolve. But so I refer to her as a she, personalize my waves, but they initiated, it was already over Central Western Africa when I started to run the model. So it runs here with a 15-kilometer global grid horizontal resolution. It's not 27 levels, it's actually 55 vertical levels. And so, again, although it's a global simulation, I really just focus in the region of Africa and Eastern Atlantic where the wave propagated. So these are the first results. Here I am showing you Hofmuller diagrams of rainfall rate on the left, and then Hofmuller diagrams of relative humidity at 700 hectopascal, that's in shade, and then the black contours are vorticity at that level. And so what we see first is that the simulations pretty much are able to represent the actual footprint of the wave when we compare it to iMerge, and to some extent the vorticity signature as well as the humidity signature at this level. So what are the differences? So the first difference is the fact that the MPAS that was initialized with GFS data was actually, compared to AERO5 and MPAS-IFS, simulation ended up being a more moist simulation, and it turns out that the wave was actually, in general, a little bit more intense than the MPAS-IFS and the AERO5. The other main difference here is the actual propagation of the wave. So in AERO5, it was propagating approximately, on average, 7.7 meters per second. In MPAS-IFS, 6.4 meters per second. And then in MPAS-GFS, which was the more moist environment, the wave was propagating at 5.1 meters per second. Now, we have seen waves that move relatively slower than the mean African easterly wave speed, which tends to be 10, 12 meters per second, but these values were definitely on the lower side of propagating the value of an African easterly wave. So this was kind of like the first hint that perhaps this particular wave was a slowly evolving system. So here I am showing you a calculation of moisture flux convergence. Now, this was one way that we went about it, actually defining the quantity in a box centered in the wave. I actually also went about it using the traditional equation of moisture flux convergence, but both ways gave me the same answer. So the answer is that here, the more negative values mean that there's more moisture input towards the center of the circulation. So the more negative, more moisture towards the center. And the solid lines is this quantity within the boundary layer, and the dashed lines, this quantity at the mid-levels. So magenta is AERO5, and orange and blue are MPAS simulations. So as you can see here, which was true for AERO5, and more so for the simulations, is that as we get close to genesis, so those times with the stars, this quantity, so moisture flux convergence within the boundary layer was increasing. So the closer we get to genesis, the more flux, moisture flux within the boundary layer. So it seems that this was actually key in the genesis of Hurricane Helene. Now, how does this translate to the vertical profile? So here I am showing you the vertical mass flux profiles. The time with the star is the time that the NHC called genesis, so the observed genesis time. Again, magenta era 5, orange and blue simulations. And just for context, I'm showing you here the location of each wave based their geographic location. And so let's first focus on era 5. So the era 5 profile goes through the typical Riemann literature review when you look at how the profile of a system evolves into genesis. So it goes from top heavy to becoming more bottom heavy as we get close to genesis. Now let's go back to the model. What is happening with the simulations? So what we actually saw in the simulation was very different from what you're seeing in era 5. We call this a bit of a double peak type of profile, where both the bottom and upper levels were competing. They're definitely stronger vertical profiles than era 5. And it turns out that after we run a genesis tracker, genesis happened earlier in the simulations than it did in actual life, and so era 5. And so in addition to that, we also saw not only a double peak profile the night before genesis, or the observed genesis, we also saw that it ended up that the simulation just had a top heavy profile from there on. And so we argued that rather than the top heavy profile being a significant feature here for genesis, it's this way because in the simulation, the structure of the system was already more mature, even over land. So we already had a more mature and intense system in the simulation that actually got to genesis faster than we actually did in reality. So we looked at what was happening at the boundary layer. We see how it reflects in the vertical. How does the actual circulation relate to moisture? So here I am showing you column saturation fraction in shade. The blue streamlines are the total winds at 850 hectopascal. The red ones are at 500 hectopascal. And so they're wave center. The first column is for era 5, and then MPAS-GFS and MPAS-IFS in the third column. So what are some of the distinct features that we're seeing here? So even before observed genesis, what we saw is that the circulation at the higher levels starts to become more and more aligned with the circulation at the lower levels. So we see how both of these centers start to become aligned very early on, even in era 5. But another interesting thing is the fact that the most saturated air is actually being advected constantly towards the center of the circulation. This was true to era 5 to some extent, but the models really augmented this. So we're seeing that in the southeast quadrant of the wave-centered maps, the more moist air is continuously being advected towards the center of the circulation. So you have a lot of moist air at the center of the circulation, concentrated where the most intense winds are. And so we're seeing that there is this advection of moisture that is associated with moisture vortex instability. Now, there's another key argument here. Where is the convection actually lying? I don't show it here, but when I plot OLR, the OLR, so the actual coldest cloud top temperatures also align with the regions of the most saturated air. So you have deep convection right at the center of the circulation. That's aiding at least this specific case of genesis. So when we look at rainfall, if it's an actual moisture mode based on the definition by Raymond and other authors, the rainfall must follow the most saturated air. And so rainfall tends to be a little bit more tricky. So what it is true here is that the most intense rainfall is co-located with the regions of most saturated air. But what we're seeing is that not everywhere that is saturated, it was raining. So is it actually a moisture mode? Can we use moisture mode theory to understand genesis? So what I do is I define a box at the center of the circulation, and I go over the moisture mode criteria as defined by recent work by Victor. And so are moisture anomalies correlated with precipitation anomalies? It turns out that 2 out of 3 of the data sets satisfy this condition. The weak temperature gradient balance must be dominating the temperature changes. This was true for all 3 data sets. Moisture controls the thermodynamics of the system. It turns out that this condition was not satisfied. Now, there's another method of calculating this criterion, and it's by using the actual phase speed of the system. So if I introduce the actual propagating speed of each of the waves that were simulated at an era 5, we find some, so they're satisfied, and then there's other ways of calculating the end mode. 2 out of 3 were satisfied. So the lower the number.
Can you remind us what the x-axis is there? Is that moist static energy on the
Yes.
x-axis? Okay.
So the lower the number, the closer it is to being a moisture mode. So what are the conclusions here? Again, the idea was never to say whether or not an African easterly wave or genesis is a moisture mode. The idea was, can moisture mode instability be used as a diagnostic tool to help us understand genesis? And I'm an optimistic person, and I say potentially, but more research is needed. Why? Because it's just only one case, but we're getting there. And this is what we're proposing. We're proposing that pre-Helene, so the wave that became Helene, was a mixed off equatorial moisture mode. So it starts off by its traditional dry dynamics. It can be baroclinic, barotropic instability. But what we're proposing is that the closer the wave gets to Western Africa, the more and more it interacts with the ITCC overland and the monsoon, the more water vapor becomes a major role in its growth. And so ultimately, moisture playing a significant role in genesis. And so we propose a tropical cyclogenesis pathway. So it's kind of a summary. The very first step of tropical cyclogenesis pathway in the Atlantic could be that systems start to become more and more of the moisture mode type. Temperature still plays a major role, but water vapor starts to becoming more relevant. And that reflects and aids boundary layer net moisture flux increase towards the wave center, enabling both mass and vorticity convergence, and ultimately helping a more vertically structured system that ultimately leads to tropical cyclogenesis. So, in summary, we find that boundary layer moisture flux was key in this particular tropical cyclogenesis event. Raymond has seen this as well in the Pacific. Tropical cyclogenesis in this case was moisture driven, and we saw that convection was co-located with the wave vortex. This was true still over land and still before genesis. So we think that particularly moisture vortex instability could be a useful diagnostic tool to understand genesis. And then finally, we propose that pre-Helene was a type of mixed off equatorial moisture mode. where we think that the closer these waves get to West Africa, and the longer they interact with the monsoon and the ITCC convection, the more moisture starts to become more important in their evolution. Take a quick water break here. So with that, I'm going to bring you in the last part of my presentation here to my more recent work. This is still ongoing work, and it's very much motivated by the results I just presented to you. So one thing that I thought was interesting is how different, there were some differences, right, in the wave that evolved in the GFS initialized simulations versus the IFS. We saw that the more moist wave had some distinct characteristics from the other one, which was the IFS initialized. So let's say we have a regional configuration of this model where I can alter the background moisture. And so I could see how in altering the background moisture, the African extreme wave evolves and eventually the genesis. So what I do is I take arrow 5 and I alter the relative humidity at all pressure levels. So I have my control simulations and I have my moist simulations where I cranked up the moisture by 20%. And I cap wherever it's more than 100% to keep things, realistic. And then I dry. I have one set of simulations that are drying out by half and then very dry. And the idea is to actually try to answer the question, how does moisture content drive wave propagation and amplification changes, especially during tropical cyclogenesis? So a few here are my preliminary results. Here on the top left, I'm showing you a wave-centered time series. On the top is the longitude position. So this gives us a sense of the propagation of the wave. Here I'm showing you 850 relative vorticity. And then over there, the wave center precipitable water time series. So that one is pretty much what we would expect. So the very dry simulations, very low precipitable water, and the moisten control had more precipitable water overall. A few things to note. So with the propagation speed, as expected from literature, the more moist wave was propagating slower overall. So those are the blue lines. The dry wave was propagating fastest. So those are the red lines, and the orange one is in there as well. And then the control simulation is the one in the green, so somewhere in between. So what's interesting here and unexpected is when we look at the relative vorticity. So this is what we see. We see that it turns out that after they cross the African easterly wave coast, it turns out that the strongest genesis was not the moist simulations. It was actually the control simulations. So what's happening here? Well, I'm trying to figure that out, but I'll show you what I got so far. So again, I'm showing you those half movers as I showed you before, rainfall rate, relative humidity, and the vorticity. And so, as expected, we see that the dry waves, the dry simulations had a harder time at starting convection, but these are the main differences that we're seeing. We're seeing that although the moist wave was moving slower than the control wave and the dry waves overall, if you look at it for a long time, as I've done, you can start to see that it is actually the control wave that ends up being able to catch up to its convection. Whereas in the moist wave, it was always too slow. It was always behind its associated convection. So something to say about that convection being a little bit out of phase with the more moist wave. So although it was growing in a more moisture-rich environment, it wasn't being able to catch up with its associated convection. here I am showing you some wave center timing composites over land. So this is for the control simulations, moist, and the two dry. So overall, we see that ultimately in the dry cases, we really end up not getting genesis, and there's really no convection being initiated. So the shade here is diabatic heating, and the counters are omega, so vertical velocity. So I'm going to focus here on the differences between control and moist. So what we're seeing here is that a more moist atmosphere favors a larger fraction of shallow convection. So we see that by that more bottom-heavy type of structure and weaker updrafts for the moist simulations. And this was true at the center of the simulation and ahead. So unlike the control, we actually end up seeing more top-heavy type of structure and stronger updrafts. And so this is what we think that is happening here. We suspect that this type of shallow convection, what it's doing is supplying heating to the lower levels, but it's not getting to the mid-tropospheric vorticity associated to the wave. So what it ends up doing is pretty much disrupting the system. So you really need, for this type of African easterly wave to grow, a heating at the mid and upper levels. So more moisture actually leads to more shallow convection at the center of the circulation, which in turn we suspect it led to the more weaker genesis that we saw from the time series. So summarizing really up to this point, we see that convection in phase with the vortex can benefit growth. We saw that from my very first early work with the satellite and reanalysis, with the global simulations. But I think the key feature that is provided by these simulations, these high-resolution simulations, is that it's not just about convection being co-located with the center, it's about the type of convection. And so it has to be deep, moist convection that is co-located with the vortex in order for it to be favorable for wave growth. And so this goes a lot in line with recent work by Angel, who states that a more saturated environment does not necessarily relate to a better chance of becoming a moisture mode. So it's not only true for moisture modes, we're also seeing that it can be true for wave growth in general. So a way that we can define moisture modes is using the quantity gross moistability. So this value is determined by the omega profile, where traditionally a bottom-heavy profile is more favorable for moisture mode growth. Now in recent work by Inanwe and co-authors, where here they illustrate the relationship between the top heaviness, the gross moist stability, and the cloud radiation feedback, what they argue is that instead of the bottom heavy system, it is actually the top heavy type of system that is more suitable for moisture mode growth because of the strong greenhouse effects of the cloud radiative feedbacks. So they actually argue that it is a type of top heavy system that can ultimately help moisture mode growth. And so I'm starting to relate their results to what I'm seeing here. So what I'm seeing is that the simulations that end up being a more intense tropical cyclogenesis were the control simulations. And these were the ones that were associated with the top heavy type of structure. And so this is ongoing work. I'm open to any of your suggestions. And I'm going to end with this last slide here, which is kind of a wrap up and kind of putting everything into perspective. So broader impacts and implications. So basically, I think that all my research thus far can be summarized as follows. I think that based on what I've seen, more water vapor in the atmosphere with the changing climate does not necessarily mean that we're going to have more moisture-driven type of genesis or African HV wave growth. And so with that, here I am detailing a few key aspects of my research which I think directly link to tropical cyclogenesis predictability. The first one being the phasing of convection in African HV wave. Other people have seen this as well. It can be key for the forecaster. We provide key large-scale predictors that can inform genesis. So in the forecaster looking out for these specific conditions, it can add up to maybe 4 to 5 days of predictability. So when you see a wave initiating over Eastern Africa, forecaster, be on the lookout. It can be a potential candidate for genesis. And then finally, boundary layer net moisture flux can be a great predictor. And we can start thinking about diagnostic tools like moisture mode and moisture vortex instability, or the stratified stratiform type of conceptual model similar to moisture vortex instability as diagnostic tools for tropical cyclogenesis. And so with that, I thank you for your time, and I'm glad to take any questions.
I'd like to open it up for student questions first. Ian.
Yeah, thank you so much. Very interesting and cool to see an application of work that's going on in the department. I guess the question comes from a bit of naivety to those those efforts from Angel's group, but it strikes me from looking at the 3 panels with the moisture and the lower tropospheric and the upper tropospheric vortex, and how the vortexes are out of phase and then in phase with one another. It strikes me as not dynamically particularly different than the tropical transition problem discussed by something like Lance Bozart's group at Albany. So I'm wondering, the point then, I guess, is that his group attacks it from a completely different dynamical framework through PV and what I guess you consider more dry dynamics, but it includes diabatic terms through the PV erosion. So I'm wondering if you can speak to when to apply which perspective. There's 2 perspectives here, one that I'm familiar with and the one presented here. I don't know that either of them are more or less right than one another, but what would motivate me to extend over, and what would motivate you to extend over to more of the dry dynamics?
That's a great question. What's your name?
Ian?
Ian. So I think that they're not far, they're very much related with each other. You can think about this as the PV typist perspective as well. For example, the paper that I mentioned, James Russell, which ends up coming with the same conclusion as Angel, they do a PV budget in which they actually see that those maximums in PV anomalies end up becoming vertically stacked. So really, I think they overlap greatly, and I don't see them as being 2 different types of ways of going about it, but they definitely relate to each other. So I would say, just like I just look at raw diabatic heating, yes, that relates to the dynamics, and PV is a great quantity to relate both dynamics and thermodynamics. So I would say it's just another way of getting to the same conclusion, but very much relate. I hope that makes sense.
In the extratropical transition, it's not vertical stacking so much though, right? Or
I'm thinking of the tropical transition problem where you isolate a mid-latitude cold core structure, you reduce the column stratification greatly, and then it stems then from the
ARC interaction.
convection that, the ARC convection that occurs beneath it. So you have extremely low column stratification, and the convection just grows beneath that and erodes the PV a lot, eventually yielding a tropical cycle. So I think of them dynamically as very similar, but the frameworks are very far removed, but they're not really.
They're not really, because you're talking about bottom top type of growth, which in essence comes about when you have a deep convective cores, where they start off from the boundary layer and feed from the moisture incoming within the boundary layer and grow to these very high stratiform type of structures where the maximum PV overlaps with the maximum of diabatic heating. So that's another way of thinking about it, right? Where you see the maximum in diabatic heating rates are usually overlapping maxima in PV anomalies. It's a source of PV, right? The diabatic heating.
Another question from students? Yeah, go ahead.
I know you skipped over this, but can you talk a little bit about how well the MPAS simulations did compared to observations, and if there are any differences like affect your interpretation of the model results?
Yeah, that's a great question. And yeah, so MPAS does pretty well with the large-scale African easterly wave structure, right? It's able to really represent that structure. When we get into the convection, it does a really good job at actually producing the convection associated with the wave. Now, when we go into actually pinpoint the differences, there's going to be differences. And especially with ERA 5, because ERA 5 has overall, it's run with convection parameterization, so it's going to differ from what we're actually seeing here, which is high res. But in terms of comparing it with parameterized MPAS and parameterized ERA 5, they're pretty similar. So it does a good job at weather-related features.
It feels like you're treating, or from what you're presenting, the moisture and vorticity, they go separately and they have their own wave speed. I think there will definitely be a feedback between the moisture and the dynamical vorticity. And can you explain on that how the feedback goes?
Yeah, no, there's definitely a feedback, and what it seems to be the case here, what I'm arguing in the last work, is that the synoptic scale wave in the moist simulations was propagating very slow compared to the convection that was moving closest to it, right? So it turns out that when you look at it from the map view, the convection was always ahead of the trough for the moist. So it was evolving slowly in a more moist environment, but the convection was always a little bit ahead. It wasn't overlapping with the vortex. For some reason that I'm still investigating, the control simulation was actually moving a little bit faster the wave, and it was catching up with the convection. Now, these are at different scales, and the backwind shear over Africa plays a major role in the propagation of these waves. And so it can be playing a different role at the synoptic perspective versus the MCS perspective. But overall, yeah, that's a good question. I think looking at the background shear and how it related to the convection versus the wave could be really insightful.
Other questions? Yeah, Matt?
This whole system seems like almost like a finely tuned railgun or a cannon where you have to get the fuse right, the fodder right, the tamping and everything. You mentioned the role of Eastern Africa, and it seems to be beneficial. I'm trying to follow your interesting arguments. Is this a useful way to pose a question that, what is it about East Africa and the growth through barotropic arconic instability that's drier perhaps, that really prepares the structure of it so that it can become a moisture growing mode, preferentially?
Yeah.
Is there something about its structure, like a 1-2 punch or something?
That's a really good question. Yeah, no, and I have thought about it a lot. I think it comes down to the fact that over Eastern Africa, when you initiate these waves over topographic regions, at the same time, you have convection being initiated. So you have waves that can be perturbed by the jet, as we know it traditionally, but you also have African easterly waves over Eastern Africa that come about from topography. At the same time that this wave is being perturbed in the atmosphere, you also have convection generating by orographic uplift. So I suspect, and this is something I have not looked into in detail, that is the combination of having that extra oomph from the convection also being generated over the region that is helping these waves kind of have that first push. But that's just a suspicion.
I haven't heard of the Amera Mountains before.
The Amera Mountains used to be called Darfur,
Okay.
and they recently changed their name.
Okay.
Yeah.
Yeah, really interesting, Kelly, and I hope you can forgive my naivete in proportion to my interest. Bullet point number 1, the African easterly waves that become increasingly more in phase with MCSs are more likely to develop in tropical cyclones. That makes it sound like these two things have a relationship that's completely passive. But what if they don't? What if it's the MCSs that are spawned by their relationship initially with an African easterly wave that are the ones that fit that category? Is that a different kind of MCS over East Africa?
That is a great question. And that's something I may not be able to answer because that would be going back and seeing what are those MCSs that initiate at the same time of the wave and stratify them from those MCSs that become coupled to the wave as they propagate.
Yeah, right.
Right? And you're right, it could be different characteristics and might be honing down into why they actually become more favorable, for genesis. So, that could be a great question.
And are there disturbances that migrate westward from the Arabian Sea that perturb the African easterly jet?
I haven't looked at the Arabian Sea. As far as I've gone eastern-wise, I've gone up to the Somali jet. Okay. So over the summer, that was another key predictor, actually. I don't have it here. But that Somali jet actually increases for the composite of the developers.
Oh, interesting.
So we actually see that there's more winds blowing over the Ethiopian highlands due to the Somali jet, which initiate more convergence.
Yeah,
and more,
that's very interesting.
Yeah.
Thanks.
I have two questions. So one on the science and one in the model. Actually, you have the plot that I want to ask about. But first, you say here more water vapor in the atmosphere with changing climate does not necessarily signify more moisture-driven TCGs and AEWs. Can you say something or imply something about the intensity through moisture modes?
I specifically did not say because because I see that the more moist simulations ended up being a weaker genesis. I don't want to say that this is what's actually going to become about, right? Because in the end, I mean, I'm thinking Clausius cloud, more temperature, more moisture, but that's not necessarily going to happen everywhere, corner over Africa, over the Eastern Atlantic, that this was going to be true, right? In the parameterized convection, the more moist simulation was more intense. In the resolved convex simulation, the more moist simulation was weaker. So there's still something to be said about how the models are resolving the moisture interactions here. So I don't want to say anything about intensity.
Yeah, no, but I find it really interesting because it's the same thing when we talk about hurricanes and how they're strengthening. Like you cannot say anything about numbers related to climate, but you can talk about intensity and how intensity relates to climate change.
Right.
But I was kind of wondering and thinking about those lines. The other thing is that plot that you have on the left, I think it's slide number 11.
Mm-hmm.
So the yellow line and the blue lines. The yellow line is MPAS-GFS.
MPAS-IFS is orange.
IFS, and that's at the boundary layer level,
Within,
right? Do you know what drives the difference between them? Because it seems that they kind of look very similar at the end and at the beginning, but then there's a big, Is that a model initialization problem, a data simulation problem?
I think these are surface interactions that the model is just playing it differently with the different type of data set. And so over here, they're crossing a little bit of topography. I believe it's the Guinea Highlands.
Okay.
And the models are just doing different things. And you can actually see it in the track too. They kind of like split and then come together again in relation to this time series.
Okay.
So I think it's related to how the model is resolving the surface interactions and the topography interactions.
Yeah, thank you.
Right.
Your moist and dry experiments seem a little counterintuitive to me. What if instead of moistening or drying the entire column,
you just did an experiment where you moisten the boundary or something like that.
Yeah.
That might be a little more realistic, I don't know.
Yeah, I
Have you
mean,
thought about that?
that's definitely another way to go about it. When I first thought about it, I wanted to alter everywhere to see just how the model just evolves and goes back to the basic state, and how that translates to the wave growth and genesis. That could be another interesting question. Whether or not the output is going to be different, I don't want to say, because it might be the same outcome, and then, but it could be another interesting experiment for sure, just moistening the boundary layer. Yeah, thanks.
So this is all really interesting. I'm kind of like trying to synthesize all the questions that I've been doing here. And so my question to you, and this is not typically a question, I'm kind of just shooting a potential idea of how this might all be interconnected, is that I think there's something to it to what John just said about I think that the developers, that it's not that there's an MTS and a wave that are aligned, but there must be a coupling. They're coupled in some way or form. And my thought is that maybe this is where it relates to what you've been finding, that this flux that's coming from the wave is feeding into the MCS, and that's kind of like keeping it on. So that the whole thing just evolves as a single entity. And my thought about this is is it possible that when you moisten the environment, it's just a little too moist, because then the wave dynamics are not really doing this flux into the MCS as efficiently as you would expect? Kind of if it's just a little dry, in which case the flux would create a single kind of bubble of highly moist air with a lot of MSE that's centered near the center. I'm wondering if this kind of situation in which there's a coupling mechanism that we are missing that really is the explanatory behavior here.
Yeah.
And not necessarily how much moisture is how much the entire thing is, but how much the wave can influence the distribution of moisture itself.
Right.
I
Yeah.
don't know if that makes sense.
That makes total sense, going back to John's argument, your argument, and going back to the actual start of the wave, right? And it might just be that a wave that initiates at the same time as a convective event that is close to it. It's just prepped better, and it's what is actually supporting its propagation and ends up being a tropical cyclogenesis. But yeah, that's a great question, and it might be the case, yeah.
Yeah, I have one quick question, because I come from a parametric background, and I have seen model experiments where they actually tweak some parameter to an unreasonably high amount and see that how that causes chaos in the system. Have you thought about your moist experiment to moisten it so much that it's unrealistic, but that might help answer some of these questions?
Yeah, moistening a little bit more than 20% was being very unrealistic. To the point that I was I don't understand what's going on here. It could be a way to go about it, but I would have to think about how much is too much, right? Already doing 20%, I was capping to 100 in a lot of places, right? So I would have to think about how to perturb. But the reasoning behind doing an ensemble of different cases was to actually make sure that this is not just random, right? So I think we ended up using a total of 13 simulations, so not too bad. Not climate, but yeah.
Thank you.
Enough for MWP?
Yeah.
Still inside.
I'm not raising my hand.
Yeah, I was honestly watching yours.
No.
I have a question for you. It's a little more broad. You were sitting off the west coast of Africa forecasting these every day. You flew the waves. Were there aspects of that experience that reinforced ideas that you had from your research, or could maybe throw a wrench in some of these ideas from that perspective?
Yeah, and that's a great question. And just talking today with your research group and what we're seeing with CPEX, for example, Research Flight 7, we saw that convection was being generated ahead of the wave vortex, but the wave was ultimately weak over Eastern Africa. It was not supporting the ultimate development. It ended up being potentially a developer in the Caribbean, but at that time, if the convection was co-located with the vortex, I wonder if we would have ended up seeing some intensification. So to answer your question, I didn't see it directly. There was a lot of cell events as well, so there was a lot of dry air intrusion in a lot of these waves that we flew, but we did see this out of phasing with convection, and I think it could hint to why it did not develop then, and it did in the Caribbean.
Thanks. All right, one more question from Matt, and then we'll.
I'm sort of naive about the theory of this. Is there any benefit to thinking of this in terms of a critical surface? You know, for waves in mean flow, you have waves that are absorbed and emitted at a critical surface. In this problem, it would be C is the phase speed of the wave, but U might be like the speed of the convergence pattern or MCS or rainfall. And if they're in phase, then you have a long time for them to interact and maybe amplify. Is that a reasonable analogy to think
Yes.
of a critical surface?
That is a reasonable analogy. The more time the moisture and the rainfall is interacting with the vortex, the more favorable it is for the ultimate coupling system. Yeah.
All right, let's thank Dr. Núñez Ocasio again.